I'm still celebrating the Bears. So, round two, second video for me today. I know you're watching these on different days, but if you're like, wow, Ms. Butler, do you not have any other clothes? No, it's because I'm making them in celebration of the Bears' first victory of the 2020 season. Anyways, today you're going to watch this video on differential rate law. So we are going to try to actually solve for a rate equation of a reaction given certain types of data, actually certain data from multiple trials of the experiment. So just to review, you saw this scary looking equation, but remember, here's kind of what it's getting at. You're going to have a negative sign if things are disappearing, so reactants. You're going to have an overall positive rate if things are appearing. We can measure rate by the change in concentration over the change in time. And then also, if we know the rate, the instantaneous rate of one thing in the reaction, and we have a balanced equation, there's a stoichiometric relationship between the rate of one thing and the rates of the other things. So in case you need a recap, here's what we've learned so far. Kinetics is the rate of reactions and the steps that occur in the reaction. There are 4 ways that we can change the rate. We saw that in our demo. We can increase the temperature, we can increase the surface area, we can add a catalyst, or we can increase the concentration. Rate is the change in concentration divided by the change in time. The rates of the reactants and products are related by the stoichiometry of the balanced equation. So I know we saw that scary equation, but here's a balanced equation we looked at last time. The rate of appearance of O2. So O2 will appear at 1/4 of the rate that NO2 appears, because it's a 4-to-1, and it'll appear at a rate half that N2O5 disappears because it's a 2-to-1. The only the relationship from the stoichiometry is what we're looking at here. Any other rate information, like what is the rate of appearance of one of those things, that we have to just determine by experiment. So yes, once we know one, we can figure out the other things in the equation, but to actually figure out that first one for the first time, what is the rate of disappearance or what is the rate of appearance, we have to do an experiment. We also learned that the instantaneous rate is something that we can figure out. It's the rate at a specific time, and it can be found from the slope of the tangent line, and this has to be from the concentration versus time plot, and then whatever time you're looking for. And then the initial rate of the reaction will be the rate of the reaction at t=0, so the slope of that tangent line at t=0. So hopefully that's a good recap of what we have seen so far this week about kinetics. Okay, so this says reaction rates also depend on concentration. The rate laws for most reactions have this general form. So this general form right here, I need like a highlighter. This general form right here, if I ever ask for the differential rate law, this is what I'm looking for. This is the equation for differential rate law. So rate equals some guy K times the concentration of one reactant to a power, the concentration of another to a different power. Those exponents are called the reaction order. So M and N, this guy here and this guy here, these are the order, and they are only determined through experiment. Determined experimentally. Okay, so we would say M is the order with respect to reactant 1, N is the order with respect to reactant 2. If I add those two exponents together, we get something called the overall order of the reaction. And then we have this guy K. This is called the rate constant. And I'll show you how to solve for that. Well, I'll show you how to solve for M, N, and K in this video. All right? Okay, for this first problem, I need you to sit on your hands right now. Put your pencil down. You are watching. You are not writing. I need you to work with me. I'm watching. I see you. You're sitting on your hands. You're going to just watch and process. And I promise there's plenty for you to do in these notes. Okay, here's how it's set up. These are reactants, NH4+, NO2-. These are reactants, and what I did is I measured the molarity in the first trial, or the first experiment, 0.01 and 0.2, and then I measured the initial rate of reaction. How fast was it going? Then, when that experiment was done, I did the experiment again, but this time I have a different concentration of NH4+. So, we're going to try to find the rate expression, which is that equation, rate equals K times the brackets to the power, brackets to the power. That's what we're going to try to do. Notice what I wrote in red here. We can ignore NO2 minus because it is the same in both experiments. It is not changing. So I notice that the rate changes in those experiments. What I can say is that the rate being different in experiment 1 to experiment 2 is not because of NO2. I know that because NO2 didn't change, right? So this difference in rate has to be because of this guy. So let's focus on ammonium, which is that NH4+. If you look from experiment 1 to 2, NH4+ doubles. Right? From here to here, we double. What does the rate do? Well, from here to here, we go from 3.2 times 10 to the negative third, 6.4 times 10 to the negative third. We also double. So my goal is to figure out the little exponent, N or M, for NH4. Here's how we do this. I know that NH4 doubled, so that's the 2, and it's going to impact the rate to some exponent, and that must equal what the change in rate was, which was doubled. So this side here represents NH4 doubling, and this 2 represents the rate doubling. So we have an exponent. 2 to the what equals 2? Well, I know 2 to the first is what will equal 2. So that exponent, x, is 1. So now I can write my rate expression. Rate is equal to K times NH4 plus to the exponent 1. There's my rate expression that's otherwise known as the differential rate law. Good job sitting on your hands. We're going to do one more. Here it is, one more time from last year. All right, same thing here. Look at the directions. No writing, just watch, because this one's a little more complicated, and this is what I'm going to ask you to do in the next problems on your own. So what I see is I have reactant A and I have reactant B. None of them stay the same the entire time. So we did 3 experiments this time. We have a rate for each. Okay, so here's what we need to do. We need to find some combinations where maybe something stays the same. So what if I look at experiment 1 and 2? Here's what I notice in experiment 1 and 2. The concentration of A is constant. So that means it is not impacting the rate. The concentration of B doubles. So from here to here, we doubled. And what does the rate do? Oh, it is also constant. Interesting. So because concentration of A is constant, we don't need to include it in our equation. So what we actually, maybe I will. That'll help us with some harder ones. Because A is constant, we are going to put a 1 there times. What is B doing? Well, B doubles, so 2 to the x is what B is doing, and that's going to equal our rate, which our rate is also constant, which is a 1. So this represents A, this represents B, this represents the rate. So we can then solve for our x and say that x is equal to 0, because 2 to the x equals 1. When we're solving for anything raised to a power and it equals 1, that means the exponent is 0. So that will be the order with respect to B. Right? Because this was all about B, we were solving for that. Now let's do the same thing, but find one where B is constant. Experiment looks like 1 and 3. So in this one, concentration of A triples from 1 to 3. Concentration of B stays the same from 1 to 3. And what does the rate do? Let's see. From 1 to 3, Ooh, interesting. The rate nines itself. So on this one, I'm going to show you the way we normally do it. When something's constant, I don't even put it in this equation, right? Because timesing by 1. So let's just look at A. A tripled, so 3 to the x equals, and what did the rate do? It 9'd itself. So this would be A. This would be the rate. Again, if we want to, we could also say B stays the same at 1. This would be B, but you see why that's unnecessary when it stays constant. Anyways, we solve for x. Careful, that's an exponent, so what does it need to be? Well, 3 squared will give me 9. I know 3 times 3 is 9, but that's the same as 3 squared. So x is 2. This is the order with respect to A. So now, let's write the rate law. Well, the rate is going to be equal to little k times the concentration of A squared times the concentration of B to the 0. The reality is we don't need to write B to the 0 in our rate expression because we know that's the same as 1. But for now, if that helps you so you don't feel like you're leaving something out, go for it. The next follow-up question that I can ask is to solve for the rate constant okay. So all we do once we have our rate law, which we said was rate equals K times the concentration of A squared times the concentration of B. All we do is pick one line from the table. So I'm going to look up. I see that first line. That's what I'm going to choose. It doesn't matter which one you pick. In fact, if you pick the first one and your partner picks the second one, you should get the same answer. So my rate was 2.83 meters per second equals K. Well, what was the concentration of A? It was 0.273 molar squared times B, 0.763 molar to the 0. And when I solve, I get K is equal to 38.0, and my unit would be molarity to the -1, seconds to the -1. That's a funky unit. I wonder where it came from. Let's look. That's the follow-up question. So little k, this rate constant, is going to have a unit. And remember, I just plugged in this equation. Rate equals k times A squared times B to the 0. And so here's what I really did. If I plug it in terms of units, rate was concentration per time. I'm looking for K. And then what I did is I took molarity squared times molarity to the 0. Well, to get K by itself, we know that this drops out and it is nothing, because that's anything to the 0 is just 1. So to get K by itself, what I really need to do is divide both sides by molarity squared. So divide this whole side by molarity squared. Well, what happens when you have molarity on the top and then you're dividing by molarity on the bottom? We know that one of those is going to cancel, but the other one's going to stay on the bottom. So I'm left with m to the -1, and don't forget that time unit is also on the bottom of the fraction, so that's going to be seconds to the -1. And that's where my unit for K came from when I plugged it in here. I was just canceling out units to get K by itself. So that's interesting. The units for K are something we need to know and solve for, but they're also going to be different depending on what the order is for your reactants, right? Because if this were something to the first, the order of 1, that we would have a different unit for K. Again, here's that problem solved out one more time if you want to actually pause and write it down now. Okay, now I'm going to actually let you write. Here's a different problem for you. I want you to find the rate law, so that's the rate equals K times this guy to this power of this guy and this power. I want you to solve for K, and then I want you to get the correct units for K. I do have a hint for you. So if you look at the rate, it's mole/liter minute. So that's really the same because mole per liter is the same as capital M. And then per minute, that's just the time on the bottom. So your textbook does this as well, but my advice is anytime you see mole per liter minute, make it molarity. Because once we get into our units for K, sometimes it's molarity to the -1, which is written as liter per mole, right? It's just flipping that fraction, and it can get kind of confusing then. So anytime, even in the textbook, I see mole per liter or I see liter per mole, I either do capital M or capital M to the -1, just to simplify things so there's less going on in my units. Okay, so hopefully you saw that in experiment 1 and 2, OH minus doubles and the rate doubles. So we have an overall order of 1 because OH doubles right here. We're going to solve for how that impacts the rate. The rate doubles, so that's going to be first order with respect to OH. Then in experiment 1 and 3, ClO2 doubles, but the rate 4s itself. So hopefully you got an order of 2, and here's my rate expression. You can pick any line you want from the experiment to plug in and solve for K. And then here are my units for K. Molarity to the -2, minutes to the -1. I made a note. The overall order of this reaction is 3. So it's first order with respect to OH minus, second order with respect to ClO2. Overall order, 1 plus 2 is 3. That might help us with these units if we want a shortcut instead of trying to cancel out units every time. Okay, so here's my trick. If the overall order, when you add the exponents, is 3, your units for K are going to be concentration to the -2, time to the -1. If the overall order adds up to 2, it's going to be concentration to the -1, time to the -1. If the overall order adds up to 1, it's just going to be time to the -1 as your units for K. And if the overall order is 0, then it's going to have the same units as rate, right? The units for rate are concentration divided by time, so this is also the same as the units for rate. But so that should be a little trick. I always think of it as molarity is 1 less in the negative version, and then time is always to the -1, right? And unless it's 0 order. So hopefully that helps you. Otherwise, if you forget, you can always cancel out units. The way I showed you in that first problem that we solved for K, showed you how you can plug in just the units and get K by itself, and that will help you figure out what the units are. But shortcuts and tricks are nice, so you don't have to do that every problem. All right, let's do this one together. So you do have permission to write with me. So I see 2 different things. Let's look at experiment 2 and 3. And I see that the concentration of NO is constant. The rate of O2, from 2 to 3, it actually halves itself. What does the rate do? I would have to plug this in my calculator, so I'm going to take this, because for the O2, I took this one divided by this one, and it cut itself in half. Other way around. This one by this one, right? Either way, I saw it got itself smaller, right? This divided by this. Let's do the same. This divided by this, and I should see that it also halves itself. Because -1 is bigger than -2. So we got smaller, we cut in half. There we go, that makes more sense. Okay, so let's look. O2 halved itself, and so did the rate. So that means my exponent must be 1. So in terms of O2, my order is 1. Now let's look for the maybe where NO changes. So for experiment 1 and 3, the concentration of NO doubles. The concentration of O2 is constant. And my rate looks like it 4s itself. I would have to double check, but that exponent's the same, so that shouldn't mess me up. Yep, 4s itself. So NO doubles 2 to the x, and the rate 4 is itself, so that means my exponent must be 2, because 2 squared gives me 4. So let's write my rate law. Rate is equal to little k times the concentration of O2 to the first and the concentration of NO squared. So that is my rate law. We can solve for the rate constant. Pick any experiment you want. 1.41 times 10 to the negative second. Concentration divided by time times K times 0.0125 molar to the first and 0.0126 molar squared. I got K equals 7,105, and because its overall order is the third, that would be molarity to the negative 2, time, which is in seconds, to the negative 1. One thing I notice, sometimes I'm going to give you minutes, sometimes I'm going to give you seconds, so always pay attention to what the unit for time is. So if that went a little too fast, pause the video. Here's that answer and work written out for you one more time. All right, last one. I want you to try this one for me. So give it your best shot, and I will put up the answer in a second. So pause the video, give it your genuine effort. It looks like we got 4 experiments, but still only 2 reactants to work with, so you should be able to handle this one. All right, here's my answer. So I said I noticed that in experiments 1 and 3, the BR2 2.5s itself, and the rate also 2.5s itself. And like a good way to figure that out when it's not so obvious. So experiment 1 and 3, right? If you take 0.5 divided by 0.2, you'll see that it's 1.5, and then do the same thing. 60 divided by 24, 50 divided by 0.2 is 2.5. 60 divided by 24 is 2.5. I think I said 1.5 on accident. Just ignore me. But anyways, 2.5 itself. So 2.5 to the x, 2.5, that's 1. The next one, experiment 1 and 2, is a little trickier because this guy, NO 2.5s itself, but the rate 6.25s itself from between experiments 1 and 2. So we're going to take 2.5 to the x equals 6.25. Well, how am I supposed to know what that is? Like, obviously, I know 3 squared is 9 and 2 squared is 4, but this one's not so obvious. We'll just do a little guess and check. If x were 0, anything to the 0 would give me a 1. If x were 1, 2.5 to the 1 would be 2.5. What if it's squared? Well, turns out that 2.5 squared is 6.25. So with respect to NO, the order is 2. So here's my rate law. Rate equals K times NO squared times BR2 to the first. The overall order is 3. So I want you to start anticipating the units for K before you even solve. I see that 2 plus 1 is 3. The overall order is 3. So before I even solve for K, I know my units are going to be molarity to the negative 2, S to the negative 1. And then I can pick any reaction from the table that I want. So don't worry if you didn't pick that experiment. You can pick any one. We should still get the same answer. And I got 12,000, and then my units are matching what I anticipated above. Okay, hopefully that was a good exposure to the differential rate law. We are going to do a practice packet in class next week to give you more experience, and then you have your problem set as well where you are practicing these for homework.